Hello again, it's Lecturer Joe here, and we're going to take our electrical theory a little bit further here with lesson 3. Okay, now we're going to have some fun with our water pipes again because now we have a strange arrangement whereby this middle section of the pipe, there's a T-piece here, a connector that's been added here and here, and the middle section of the pipe there are actually two pipes. There's a thick or fat pipe here and a thin pipe here. Now, let's suppose that the flow rate out of the end here is still 2 litres per second. In other words, we can fill this 10 litre bucket in just 5 seconds. Well, we know from back in lesson 1 that if the flow rate here is 2 litres per second, the flow rate here must also be 2 litres per second. Now the water flows along here and then it splits, and some of the flow goes up this way and some goes down this way. Some flows along there, some flows along there, and then they join up and flow out here. Now the question is, we know that the flow rate here must be 2 litres per second, the same as it is here, because if 2 litres leaves the end of the hose every second, there must be 2 litres entering the hose from the tap every second. The question is, what is the flow rate here? If we were to put a flow meter in there, and what is the flow rate here if we were to drop a flow meter in there? Now might be a good time to pause the video for a few seconds and have a think about what you think the answer is. Okay, let's take a look at it. So we know the flow rate here is 2 litres per second inside the pipe, as is the flow rate here. The question is, what is it in this pipe and in this pipe? Well, the key here is that the water that flows in here splits. Some of the flow goes this way, some goes that way. So the total flow from left to right must still be 2 litres per second, but that means that this number and this number added together must give you 2. So it could be that the flow rate here is 1 litre per second and the flow rate here is 1 litre per second. However, that's unlikely, and the reason that's unlikely is because this is a wide pipe and this is a narrow pipe, and it's much harder to flow through a narrow pipe than to flow through a wide pipe. So probably a more sensible split would be maybe 1.5 litres per second there and just 0.5 litre per second through the bottom. So these are sensible answers. There's no correct answer here, of course, because it's just a diagram we've drawn up, but the principle is that firstly the flow rate splits because of this T-piece. Here we've got one pipe, but then it becomes 2. So we now have 2 flows, and those 2 flows must add up to the flow that went in. 2 litres per second flowed in, and there's still 2 litres per second flowing from left to right as you go across, and they join up to give 2 litres per second here. The other thing that we need to notice and bear in mind, because this will come into play with the electrical circuits as well, is that this flow rate is much bigger than this flow rate because it's easier to flow through the wide pipe than the thin pipe. And the reason for that is because the thin pipe has, this pipe being narrow, it has a high resistance. A high resistance to flow. So where we have the high resistance to flow, we've got the reduced flow rate, and where we've got a nice easy path, we've got the much larger flow rate, and those two must add up. What flows in must flow out. So let's compare the water system with the electrical system and see what the comparison is. Here we've got a single pipe, splits into 2, back into 1, thick pipe coming in, thick pipe going out, but here where it splits we've got a thick pipe and a thin pipe, and you know that through a thin pipe there's a high resistance. High resistance to flow because the pipe is narrow. So let's look at what the electrical equivalent of this is. Here we've got a wire coming in with a certain amount of resistance. It then splits into two, each of which has some resistance and joins back into one. And similarly to the water system, the flow is from left to right in this diagram. So you can see here where the pipe was thick, I've said we'll call the resistance 1, and where the pipe's thick here, the resistance is 1, and where it's thick here, the resistance is 1. But where the pipe was thin, it's like having an electrical resistance of, let's say, 3 or 4. So the resistance is high in the electrical circuit, so you get a low flow through here compared to the flow we have through the top. Similarly, in the water system, we get a high resistance, which gives us a low flow rate through the bottom and a higher flow rate through the top. And in the drawing we had before, we assumed we had a flow rate here of 2 litres per second, a flow rate here of 2 litres per second, and in between, on the top, 1.5 litres per second, and on the bottom, 0.5 litre per second, where these two have to add up to give you 2, and the large flow is where the resistance is low. On the electrical circuit, the equivalent would be measuring a flow here of 2 amps, a flow here of 2 amps, and a flow here of 1.5 amp and 0.5 amp. Again, the larger flow goes through the smaller resistance, resistance of 1, resistance of 3. Lastly, in this video, I want to point out that this electrical resistance has a unit. It's measured in ohms. And rather than writing that whole word, we normally just use the symbol for it, which is this. So really on this diagram, I should have said the resistance here is 1 ohm, 1 ohm, 3 ohms, and 2 ohms. So bear that in mind. We're going to be using this a lot in our future electrical circuits. So the resistance is measured in ohms. Okay, that's all for this video. So tune in again.